Okay, probably at this point we can start. So please, Maurizio, go ahead with this fourth lecture on machine learning.
So today we discuss graph nets, which are more, let's say, cutting edge topic in the sense that it's relatively new. It's something that you would say took starting to appear on people's radar 2 or 3 years ago, and then it's getting momentum now. And particularly in high energy physics, it seems to be particularly suitable. So the tutorial of today is gonna be substantially more complicated. So I'm not sure how we're gonna do that. Most likely we will just go through the code. It takes a lot of time to train. I already trained it. I pre-trained it in order to show you the result, but maybe we just go through the code. So, and it's really a very first example of what people, when they do advanced things, do in practice, which is effectively, well, this is called tensor programming or probabilistic programming. I think people like to call it like that. So just a reminder, we said so far that, and this is true in general, that typical deep learning architecture, because it scales better with input dimensionality, it gives its best when processing raw data. And a typical network would then be structured into 2 steps. One is the feature engineering part, which typically has some architecture that it's designed to fit the data format that comes in. And then the features which are produced, typically in the form of a one-dimensional vector, are given in input to the downstream step, which is the task-solving classic dense neural network, which on the other hand, the 2 steps on the other hand are trained simultaneously. Now, what about irregular data? So the underlying assumption so far has been that your data are structured in some regular and ordered way, which could be just because you have an array of pixels like in an image, or you have a sequence and so on. But let's say that your data are just a set of items, and each item has its own set of features that characterizes it. Typical example, you could imagine galaxies or stars populating the sky. You could just take the full list of stars in the galaxy and label them with coordinates and velocity. And that would be a set of irregular set of points. Sensors in a typical high energy physics detector. Imagine something like you see in the bottom right there. So a typical calorimeter is arranged in layers, and each layer has its own granularity. So at the end of the day, the thing that you handle is just the cells which are not, which recorded some energy. And these cells are given you as a list of items which have coordinates and recorded signal. But even, and this is actually the striking example that made graph nets became famous, molecules in chemistry. You can imagine molecules represented as a set of atoms which have their own position. So people, when they refer to this, they may refer to them as sparse sets. And typically one would say that the minimum thing you can do is the thing that you see in the top of the 2 images in the bottom part of the slide, which is you have some image, for instance, let's say a black and white image. You zero suppress all the white pixels, they're unoccupied pixels, and the other ones you just characterize them as coordinates. So each pixel is turned into 2 numbers, but only the pixels which are occupied. Typically, this also means that you're compressing your data. You could even go beyond that and just use the coordinates, but also some additional feature that characterize the pixel. For instance, if the image has some grayscale, the grayscale index could be used. If the image has colors, could be RGB. And so you see that now each pixel is characterized by a vector of quantities, and the dimensionality of the vector is something that depends on how you want to handle your problem. So once you have these sets, you want to learn from these sets, then typically, I mean, you don't have to, because there are networks called deep sets network that already handle the sets. But you can basically learn by building a graph that connects the items in your set. And then somehow try to learn a representation in which the relevant connections are highlighted and the irrelevant connections are dropped. Or if you want, what you're trying to do, you're trying to learn a metric by which things that talk to each other are nearby and things that are unrelated are far away. So not the distance in the physical space in which your data are represented, but in some abstract space. So you're trying to learn an abstract representation by which things that are related gets next to each other and things that are unrelated gets far away. And so what you want to learn is basically this abstract space characterized as a metric. And this, in some sense, is the generalization of what a convolutional neural network does, because the convolutional network does exactly this. It takes advantage of the proximity of pixels, where the proximity, on the other hand, is by construction, the physical proximity of your pixels in the image, while here it could be like a more general concept. And indeed, the most famous architecture for graph networks is what people call EdgeConv, which is a generalization of convolutional neural networks in which you have exactly the same structure. So you have this kernel that moves, but the kernel doesn't move in some physical space where your points are arranged regularly, but it uses something which is called an adjacency matrix. That is something that you learn, which is a matrix in which you fit the first n neighbors of your given item according to this metric that you want to learn. So the idea is that you connect the elements with some metric that you express as a neural network, and then you want to train the neural network to learn what's the optimal metric. So how do you build a graph? So you have your elements, and of course you can imagine to represent them on a plane like this, and the connections are connections between different objects. The connections are represented by the edges that connect the vertices. The vertices are the items in your set. And you can have like a fully connected graph that would have order n square connections. Or you could have some criterion by which you know that certain elements are connected, but certain others are not. For instance, the items in your set might not necessarily have to be objects of the same kind, but it could be objects of different kind. We will see an example soon. And so certain connections would make sense and certain connection would not, and you would just not put those connections there. It's like in a dense neural network, if you knew a priori that certain connections are relevant and certain are not, and so you would drop those. Okay, you will prune your network. Here you can do it by construction. For instance, imagine that those elements there, but let's see, we'll see an example later. You could even decide that you do it geometrically. So for instance, you connect like the nearest k neighbors in some space that can be the physical space or the arbitrary space. For instance, if you're trying to connect particles, like we did this when we were trying to learn how to subtract pileup at the LHC. So you have a particle, you would like to know if this particle is coming from the primary vertex of the event or it's coming from some other spurious collision. A way to do so is that you look at the near neighbor. Typical, you would take the radius that it's typical, the radius that, for instance, you use for jets, and then you will only connect that particle to the particles in that disk. So, but you can have different criteria. So if you have blue, gray, and orange items, maybe, and blue items, maybe in your case, blue items talks to each other and talks to the orange, but don't talk to the green. like in the example there. Another thing is that the connection can be bidirectional, which means that it's symmetric. So the way in the example, the blue talk to the gray is the same as the way the gray talks to the blue. Or it could be directional, in which case there is an order. And the examples that we're going to see are directional. Now, the essence of graph networks is the concept of message passing. So what are you trying to do? You're trying to sit in the middle of your graph, concentrating on one item of your graph and trying to gather information about that item, looking at what you know of the other items in the set which are connected to this one. So you want to create a message which you express with some function that you want to learn, and you want to gather this information across the graph, across the connections. Okay. Example, which is a very bad thing to do, so don't do it. Let's take a data set from a social media. So you have some user in some social media, and you want to know who will this person vote for at the next election. So what do? You look at the connections of this person with other users of the social media. That's basically building your graph. And then for each user, the one that you focus on and all the others, you have information. So you know the gender, the age, which kind of education, you have the likes, you have information about this person. So you want to gather information from a given person that you don't know who this person would vote for, looking at its social network and her social network. And in the social network, you might have people that you can associate to some political party because the person is very vocal, it's an active member of the party because of the retweets that the person makes, and so on and so forth. There is a raised hand.
Yes, can yes. Just a question. Sure. How more efficient is to do this with neural networks than to use some clustering algorithms that do not use any neural network?
I mean, a neural network is you can define a clustering algorithm that uses a neural network. The difference between a clustering algorithm that uses a neural network and one that doesn't is that in a typical, let's say, rule-based clustering algorithm like I don't know, anti-KT for jets, you specify a metric. Well, here you want to learn the metric. So if you know what the metric is and you know that what's the perfect metric of your problem, you should not use deep learning. So it's the same thing that I always make this comparison. So if you want to track a particle inside the detector and you know the Lorentz force, you should enforce the fact that particles follow elliptical trajectory, helix trajectory, and not guessing these through your network. I mean, things that you know should be used. So if you have a problem in which the metric is obvious, there is no advantage in using this. If you have a problem where the metric is not obvious, you can make guesses, and then the matter of optimality comes in the game. And one of problem you address the optimality is learning the metric from the network.
Okay. And I can also compare the metric that a deep neural network guesses with the one I would guess to learn if there are any relevant features that I didn't guess before, potentially.
This is the same kind of reasoning that we were saying yesterday when talking about the classifier, right? So you have features that solve your task. You want to correlate those features with those that you know are relevant to understand if there is basically the network relearn things you know or relearn something new. Sure.
Thank you.
Now, there are a lot of examples that I have. Unfortunately, there is no time to go through all of them because we could spend like tomorrow's lectures on, and I'll show you the examples of how to use graph nets. This is relatively new literature. Just like if you look at, there is a nice review. I think I forgot to put the slide. I would put it in the chat. There is a nice review on how graph nets are used in energy physics that is relatively recent. And it's, I think it's a good reading. I will send it to you there. You will see a lot of stuff there, some of which I've done. So I'm particularly keen on the fact that I think this is the thing we should be doing the next 4 or 5 years until something better comes out. Now, back to our example. So what do you want to do? You want to sit on a specific position in your graph, so on one user, and you want to gather information from the connections, and the information is a message that it would be some function of the information that you have about this person, the information that you have about the person of the connection. And so you can imagine that there is a message, some influence that the connection is playing on the person that you're focusing on. So we talk about a message as a function of the features of user one, of the sending user, and the feature of the receiving user. And so for a given user, as a receiver, you would like to gather the information sent to this person from all the others. Okay? So once you have this thing done, and then if you have a training data set, you can try to get your network capable of predicting what people would vote for. And unfortunately, this is what was done. Then typically you would then attach to this target pressure on the user, for instance, with target net ads, fake news, and so on. So this is basically what's happening on social media these days. Don't do it. Now, back to more ethical applications of AI. So how does it work mathematically? So each vertex of your graph is represented by a vector of features. You have, let's say, k features. So each item lives in this k-dimensional space. And they are labeled according to which vertex they belong to. Now, you build the graph. If you don't have any reason to think that certain connections are more relevant than others, you just do a fully connected graph. And then you build a message. So you introduce a function, G, which is a function of the sending user and the receiving user in this order. And that would would define the message, okay? And typically this function G is a function, if you know that there is a certain function that matters, for instance, if that function for some reason should be an exponential function, you just put an exponential there. But if you don't, you put a neural network, typically a dense neural network. And when you do so, you pass the message, means that you compute all these M message 1 to 2, 6 to 2, 5 to 2, 4 to 2, and so on. And then this builds a new representation of your single objects, because once you gather this message, a gathering function typically could be the average of all the messages, the maximum of the messages, or so on. This creates a new feature that you can append to the vector that defines your vertex. And so now you have a new representation of your vertex. The vertex is the same. Topologically, the vertex didn't, the graph didn't change, but each vertex now has an extended features, which could be obtained just looking at the output of this neural network. For instance, if G is a neural network with 10 outputs, now you have 10 features representing this object. Or you could just concatenate it to the initial input. But in any case, you are creating new information about this user. And then what you can do is that once you have this information, which now it's much more rich than the information you started with, because this is not just the information of a user, it's information about its social network. Then with this enriched representation of your vertex, which starts, let's say for the case of the vertex number 2, there is a vector F2, which is the initial set of information on the user, and the vector F2 prime, which is the vector of these features that we learned from the graph. You concatenate them, and this could be the input to a neural network, a classifier, that says if this person will vote red or blue. Okay. So again, you see that the structure is the same. There is a feature engineering step. You start from the graph, you build the message, you gather the message, you create the features, which are F2 prime. And then there is the task solving aspect, which is how, from the information you have about the user, initial information and gathered information, you obtain the answer you want. So, and then you can repeat this in steps. For instance, imagine that I have a graph like this one. So I have different, I have something that qualify my elements in the graph. For instance, social media data set, I can have professional links as opposed to personal relations. And so I could decide that first I gather information from the professional link, and then once I have that, I gather information from the professional relation. Or particles in an event. I could start from near neighbors in the eta phi plane, and then I could expand the attention to the more far away. And so you could start with the near neighbors. You start from your red circle and you turn it into a red square. So you change the representation of your objects, and then you consider the next one, and then you change again the representation of your objects. And you keep doing so, and you are basically expanding in these iterations the information that you have. Practically speaking, how you do this, like this kind of iteration things, people sometimes embedding into some recurrent layer. So at the end of the day, you will see that when you build a graph net, you can actually combine the kind of structure that we have seen so far into a much more complex tensor processing flow. You could say that these iterations are basically done through a graph net, recurrent net. Each item that enters into the network now is the outcome of some dense neural network. And so you bend networks into networks. So you see that this becomes way too complicated, and this is not something you do with Keras. So in equations, what is happening? So as we said, a message, you express it as a function that typically you represent through a neural network you want to learn. And your function can be a function of the sending and the receiving vertex, and maybe some features of the edge. You might know something about the connection that qualitatively defines the edge, like is the first neighbor, second neighbor, so on. And then the gathering is the kind of things that I wrote in the bottom. So you start at some iteration t, that could be t equals 0, your initial information about a given element of the graph. And then you create the next iteration, the next representation of the very same objects, gathering, in this case, through a sum function, all the messages from the other vertices that this vertex is connected to. So what you're doing is, mathematically speaking, it's sum over connections of some function m of the sender, receiver, and edge features. In our case, we will not have edge features, but you could. And then you can then combine with some other function the initial information with what you learned and create the new representation of your vertex. And then at the end of the day, with this new, at the end of the last iteration, so you do this iteration from t equals 0 to t equals capital T. At capital T, you stop the gathering information and you say, now I want to learn, I don't know, some feature. So I want to answer some question with, for instance, a yes or no answer. So it would be a classifier, and y hat is going to be a number between 0 and 1. Now you could see the iterations t that goes from 0 to capital T as the equivalent of the layers of a deep neural network. So every time you run and you learn a new function, and the function that you learn, you see that m here carries the t index, because the function doesn't have to be the very same function every time. You can learn something at the first step, something else at the second step, and so on. Typically, it is not the same function. Also because the dimensionality of HT changes with the number of dimensions. The same way you're in a dense neural network, the size of your tensor depends on how many filters you put in the previous iteration. So you see that the concepts are similar, but the arranging is completely different. Okay? So in this example, M, U, and R, so M that builds the message, U that builds the new representation of a given vertex from input from previous information and message, and R that solves the task, you express them as neural network. You don't have to, but you could. But again, if you have some knowledge of your problem such that a certain kind of function should be sitting there, you just put that function, you don't put a neural network. So in this way, people call it probabilistic programming, because it's a nice way to encode in one flow of operations previous knowledge of the problem with things that you can learn. Now, a little bit of history, as usual. So this thing started, let's say, 6 or 7 years ago, but it was very, very, very speculative. It started from Jan LeCun again, so the very same guy that invented convolutional network, that wanted to generalize convolutional network to irregular arrays. Okay, and he came out with this concept of adjacency matrix and so on. And then the breakthrough, at least in my mind, is when people started to do this, to use this to do science. So there was this paper in 2015 that was in some journal of chemistry. So their task was to introduce to have a convolutional neural network that operates directly on a graph and not on an image. They want to process molecules. And in this case, I think it was some generative. They wanted to generate configurations, not sure. But the algorithm that they have is the one on the right. The language they use to describe the algorithm is completely different than one I used. But if you look at the math, it's exactly the same. So there is a message passing there and so on. So here there are further readings that you can look at. There are, okay, so this is so these are links, so you will have links. This is the review that I was referring to, particle physics specific review. If I open it, you will see it. Maybe. Whatever, it will load and then we look at it later. And then here I put some links to GitHub applications. These are things that I have worked on. I will also, if you look into the GitHub package where these lectures are, if you look in the other directory, there is a class dedicated to graph nets that I've given to the University of Pisa recently. And there you have specific slides. It's an extended version of the slides where you have these other examples described. Today we concentrate on interaction networks. So I will pause here if there are questions. Doesn't seem so. Okay, so I'll keep going. So I start showing you this video. This is what an interaction network can do. It's not what an interaction network is. I will show you what it is later. So this was a network put together by DeepMind. It's a little bit of the structure of the network. We will discuss this later. To do, for instance, n-body simulation. So you have, your graph is basically n-bodies in a box. And you want to know the position of these bodies after some delta t time. And you do this with an interaction network. And what you're trying to learn effectively here was Newton's law, without saying the network that Newton's law is what matters. And the network is trying to learn that. And see, you want to learn how to bunch things. It's not exactly one-to-one to the ground truth, but it's very realistic with the things you see on the right, okay? And then they also did, they showed some generalization. So for instance, they train with 5 objects and then they use it with 9 objects. And then even they do like the effect of gravity on non-rigid bodies. So how does it work? It's a flow like the one that we discussed so far, except that it's not necessarily obvious looking at it. So on the right, you have the diagram of what is going on, but I'll try to describe it with the same language that we're using so far. So the first thing is that you build what is called sending and receiving matrices. So you start from a graph like the one on the top, that's simple for 3 objects. And you want to build a matrix, the receiver matrix, which is a matrix of objects versus links. And since these links are oriented, so they are directional link connections, and the self connection are not included, you have a matrix which is going to be n rows, and the number of columns is going to be n times n minus 1. And the entries of this matrix are zeros or 1. They are zeros. They are zeros everywhere except for, in the case of the receiver matrix, for the object, for the row that received a given message carried by a given link. So, for instance, in the graph that you see above, you see, for instance, that the object O1 receives the link E4. So the entry between O1 and E4 is 1. And similarly, O1, the other message that O1 receives is E5. And so E5, O1 is 1. The other entries in the row are 0. Okay? This matrix is basically a convenient way for you to do the message gathering as a matrix multiplication. You will see it in a sec. So how does it work? It's this very complicated diagram here. So the first thing is that you start from an input, which is features. Each row is a features, and each column is a constituent, it's a vertex in your graph. So it's transposed with respect to what we've been playing with yesterday. And you will see in the code that there is a lot of transposes happening here and there. If you multiply these objects times RR and RS, RS I didn't say, but it's the same thing for the sending and not the receiving links. So when you do so, what you're doing, you're basically cherry picking specific senders and specific receivers and arrange them into a right column. So this is a nice practical way for you, once I give you a data set, which is number of constituents because I'm thinking about jets already, and features, it's a mathematical way with one operation to obtain another representation of your data set, which is a column in which I have 2p, where p is the number of features, times NE objects, and is the number of connections. So basically, this mathematical operation allows me to build a graph. It's a mathematical trick. Now, each column is a link where the first p elements are the senders, not the receivers, and the second p elements are the senders. And now I want to learn the message. So the equivalent of the M function that we saw before. And I do it with some neural network that here is called FR. FR will give you in output some array of numbers, which are the learned features. The language that they use is slightly different. They talk about interaction because they have in mind the embodied system. So the features of the object will be, I don't know, the position effectively and the mass. And you want to learn a function which is related to the position and the mass of the two objects interacting. So it's called the one that builds the interaction. Then these objects, if they get multiplied by the transpose of RR, effectively give you the gathering across the vertex. You will see, so let's, I mean, it's easier maybe if you look at these slides. So the first step builds the matrix B. Matrix B means that each object that you take in input downstream is a vector of sender and receiver. So you concatenate the sender features and the receiver features. Then you build some function FR of the sender and the receiver, starting from this vector as input. And then with that transpose operation, effectively what you're doing is that you are summing over the receivers all the FSR message that you build. And this creates the gathered information with the same language as before, except that you are doing it with a very, very specific set of mathematical operations through these RR and RS matrices that just make it suitable for a GPU if you want. And then at the very end, you concatenate these interaction features that you have built with the initial information that you had on the given part of the given particle, if it's a jet, of the given vertex, if you think generically about the graph, and you're building the post-interaction representation of the object through another function, FO that you again want to learn. So you see that all this business at the end sums up to two neural networks, FR and FO, which typically are very small networks, like 2 or 3 layers dense neural networks with 10-ish nodes each. You will see in the example that we have. But the point is that the way these networks are used across the graph, the power is in the graph, it's not in the network. This is what I wanted to say. Okay. Now, in the case of the n-body simulation, the outcome OR would be the position of the objects after a time delta t. And so the network effectively is trying to represent the embodied interaction between these objects as a set of one-to-one interactions with some function, which is the gravitational potential that you know, but the network doesn't know. So it approximates to some function FR, and then it's learning where the object will be after a little bit, looking at all the one-to-one interaction it's having with the objects around it. Okay, and it works pretty well there. So we're not building an embodied simulator. We want to have a jet classifier because our problem, remember, is this. So how do we do this? We use this very same construction, except that we only do one cycle. And after the cycle, we obtain this matrix O, which is the new representation of my NO objects. The O are the number of features that I engineered in the post-interaction representation. And then what I do is that I sum across the graph and I build a one-dimensional vector, which is information about the full graph and doesn't have any memory about specific items in the graph, specific vertices in the graph. At this stage, I have built something which I can inject into another neural network, which is the task solver that will give me the flavor of the jet. Now, if you notice, this full construction is permutation invariant. If I take two objects of the jets and I invert it, since the processing of FR and FO is per column, and since O bar is built summing across the rows of O, this full construction is invariant if I exchange the role of two particles. And this is a property that when you're dealing with jets, it's something that you want to incorporate, because this way you can get rid of the need of ordering your objects, which is something that we didn't like from the RNNs of yesterday. So this object, a neural network of this kind, is capable of dealing with sparse and permutation insensitive, if you want, permutation symmetric sets of objects, which is a nice property for a jet classifier. Now, these plots we already seen in Slack and yesterday, for instance. This is to show you that they do perform better than other stuff that we've been playing with this week, except here. So in the top right, in the top, it is at the top classifier with DNNs gets better for efficiency lower than 80%. Okay. And so I think now we're gonna try to do this. As you understand, it's a little bit more complicated than the thing we've been doing so far. I mean, when we did this, there was a paper by DeepMind about this object, and we basically recoded it. There is a student that recoded the full network, and we're gonna use the code that this student wrote as a default. As of today, you don't have necessarily to do so, because there are libraries that incorporate these and other kind of graph nets. DeepMind, for instance, built one on top of TensorFlow, which is called GraphNet, I think it's called. Now, I didn't use that because I think it would be it would not be very pedagogical to just use that. And because there is nothing magic about this construction, you could imagine to change it in infinite ways and at the end of the day, get out your own graph architecture. The idea that I want to somehow pass to you is the concept of, the central concept is the message passing, okay? So this is a little bit the summary of today's lecture. We still have 40 something minutes for the end zone, which means that in terms of time, we're good. And the question is if there are questions. Nobody's raising hands. No, there is a raised hand.
So, hello. I wanted to ask again in the beginning, you mentioned if you have no idea about the connection in your graph, you just do a fully connected graph.
Mm-hmm.
So, I mean, for example, even in our case of the jet, I mean, there would be too many connections, I guess, to do anything.
It would be a lot, yes. And indeed, one of the major challenges of these objects is the memory consumption. So where we are struggling today, for instance, in order to bring this kind of architecture to real life applications is in keeping the memory footprint of these objects under control. And but it's not completely unmanageable. People sometimes approach this with the iterations that I showed you before. So you start from the first neighbors and then you expand. But then the disadvantage of that is that you introduce some serialization processing, and so you slow it down. Other possibilities is just that you custom code how these networks get into your GPUs. For instance, coding CUDA kernels directly. In general, graph nets are the nightmare of the people that optimize the inference aspect of the problem, because typically you would basically allocate a fixed chunk of memory, and graphs basically means that you are gonna have unordered memory access, which is just a nightmare for people that design chips. Mm-hmm. It is an open challenge, and so far the answer to this challenge has been basically building dedicated processors. So for instance, there is a company which is called GraphCore. They came out with a chip architecture that is, they say it's customized to end of graph nets. It's gonna be like the GPU of graph networks. So it is a challenge, but it's not like impossible. Okay. In the example that we're gonna play today with, we're gonna look only at the first 30, I think, particles in the jet. So the most energetic 30 particles in the jet, while yesterday we played with 30. And exactly to address the point there, because Colab puts a limit on memory on us. But the paper that I showed you, the paper from which all these sizes are obtained, was done with 150 particles. On the other hand, it took a week to train the network.
Okay, so how many connections were there initially for the 150 particles?
So it's gonna be 150 times 149.
I see, yes. Okay, yeah, it's not that bad, okay.
But there are even more striking cases, like the stuff that we're trying to do with the CMS calorimeter. You start to have like 600 items, vertices of 600 items in your graph. So it is a computational challenge, but it's not an impossible one.
Okay. Thanks.
It's work in progress. If there are no other questions, I don't see any. So this is the, am I sharing? Yes. So this is the review that I was mentioning. It's written by two LHC physicists, one from Atlas, one from CMS, and researchers from DeepMind. And it has a nice introduction of graph nets. So you see some of the images that I showed you, I took it from there. And also I think that there is a fully comprehensive overview of what people have been doing with this kind of networks, the different kind of networks, and some practical examples with references to papers. Right, it's downstream. You can look at it now. So I added, where is it? Notebook 5, jet identification with interaction networks. Now, there are a few things. So this is written in PyTorch. So the initial part is the same. We are accessing the very same data sets of yesterday. Except, oh no, I was wrong. We're rendering 100 particles. I'm sorry. I thought I cut it at 30. No. We have the full 100 particles. So we're gonna play with 9,900 connections. And then we have the 16 features that we played with yesterday as well. Now, one issue though is that so a lot of time today, I'm gonna do this. So let me prepare. I'm gonna switch from the code to this. How do we do this though? Yeah, for instance. So you see that the input here is not constituents times features, but it's features times constituents. So I have to swap the axes, and I'm gonna do this a lot of time. Another thing that I'm gonna do, I'm gonna use PyTorch. So up to here, the code is modulo this swapping thing is the same as yesterday. So, but you see that, oh no, sorry, I remember that. At some point I do cut the sequence to 30 because otherwise it would be too much. Okay. So at the end, this is the data sets we're gonna handle. So it's our usual 33,500 examples for training and 16,500 for validation. There are two differences with PyTorch. One is that, as you see, the target now is a one-dimensional vector because PyTorch doesn't like one-hot encoding. It doesn't like the 5 bits as we did yesterday, but it wants the index 0, 1, 2, 3, 4, 5 for the classes. So there is an argmax somewhere. Now I don't see it, but there is an argmax somewhere. Here. Okay. This is bad because the way in PyTorch the cross entropy is implemented, it doesn't take one-hot encoding, but it wants the number that corresponds to the category, whatever. So the target is one-dimensional, and the other thing is that I swap the feature and particle index such that we have, for a given jet, we have exactly this format. Another subtle thing of PyTorch. PyTorch is really way more hands-on than Keras, is that you are really manipulating tensors, and you manipulate it at the level that you decide where to allocate the tensors. And if you want to use a GPU, you have actually to code the fact that that given object goes into the GPU. So for instance, a typical instruction is this. So I have my X-train is a NumPy array. I convert this NumPy array into so this is the full instruction, into a torch tensor, and then I move it to the device that I want to use for a computation. By default, the device is a CPU, but if a GPU is seen, which you can use this to check if CUDA is for GPU there. CUDA, strictly speaking, CUDA is the language that you use to program an NVIDIA GPU. But torch.CUDA is basically available to use a GPU. And if it's yes, the device becomes CUDA. So it's a GPU. CUDA stands for GPU here. So here, I'm just taking my data set, I'm converting to PyTorch, and then I'm moving it to the GPU. This operation takes time. We only do it once. And now, unlike our 5 lines of code, you see now that the coding for the interaction network is way more complex. I'm not gonna go through all of it, but I would like to give you a little bit the sense of it. So every time you allocate a model in PyTorch, you define a class. that is an inheriting from an n-dot module, which is basically the generic class for neural networks. In this case, for this network, in the constructor, I need to allocate all the ingredients that I'm using in this tensor manipulation flow. So for instance, I need to know how many P I have, how many features, 16. So P is P here. How many particles, N is N0, which is 30. This defines the number of connections. So unfortunately, the syntax is not the same. NR here is NE here. So it's N times N minus 1. And then here I'm defining how many outputs I want after E. So DE, I put 8. You can put whatever you want. That's how many features I want to learn if you want at this stage. And then DO is how many features I want to learn at this stage. I put 8. You can put more, you can put less. As usual, it's like for the neurons. How many targets? We have 5 targets because we have 5 classes. Then we wrote a routine that is somewhere down there, assign matrix, it's here, that builds this RR and RS matrix. And this we do it once and for all. Notice that here we're playing with the fixed length sequence. And so we can build RR and RS once and for all. If you're playing with multi-variable length, it's more complicated because you will have to do this per event and then the computation gets unfeasibly slow. So here we're taking a little bit of a shortcut. There are better ways to do this, but for the moment, let me just do this. So I define these matrices once and for all. They're allocated, they're pretty big, but they are integers, so they don't take that much memory. And notice that when I create them, I also move them to the device because I want to move all my ingredients to the GPU in order to have all the stuff on the GPU to do the computation there without doing back and forth, because back and forth is slow. Okay. The next step is, so this is something that it's a trick. The very first thing that I do in a FAR, it's a batch normalization because I would like to standardize my inputs. So to put them with mean 0 and RMS 1 without having to do it by hand. So then the easiest way is that you put a batch normalization at the beginning so that this thing is reading PT, eta, phi, whatever. Everything is standardized to have the same order of magnitude. This is something that in general helps neural network, but it's not needed necessarily. And then all these instructions here are the allocation of all the layers of FR, FO, and phi. Phi is in the other slides, and phi. Okay, so each network is 3 layers. FR has 3 layers, FO has 3 layers, and FC, which is phi, has 3 layers. And then dot linear is the equivalent of dense for kernel for Keras. This is the dimensionality, so how big is the layer in the input. So how many inputs you have, how many outputs you have. So you need to specify input and output because again, this is gonna be a flow of tensor operations. And if the output of one layer doesn't match the input of the next one, it just crashes. So you see that I enters with 2 times P, this guy here. And then I have self.hidden, I think it was 10. I have 10 neurons. So my first layer has 10 neurons. The next one has 10 inputs and 10 neurons. So I do 10, 10, 10, and I get out with 8. And similarly for the other ones. So here you allocate all your ingredients. And so basically I put on my GPU all the pieces I need to build this kind of network. And this is the constructor. And then in the forward function, which you need to say what happens, how these things are connected. And if you look at this thing, which now I'm not gonna go through all of it, but it's basically this flow that you see here. So I multiply my X times RR and then times RS. I obtain these 2 objects, I concatenate them, and I have B, it is here. And then I apply to B the 1, 2, and 3 layers of FR. And notice the syntax is slightly different here. This is the layer. The arguments are the sides of the inputs. -1 means whatever number you want. It's basically star. And this is the output dimensionality. And when I do b.view, means I'm forcing, this is me being paranoid of forcing B to have exactly this shape to prevent my code to crash. But if you take this out, it should work in any case because B is built to have that kind of dimensionality. But whenever you see this b.view, it's me being extremely paranoid. But the syntax is this: self.fr calls this object, and it's applied to the thing that is in the middle. And the activation function gets in the output. So you do activation of layer of X. So it's a little bit of a different syntax. And then you do this in the sequence, and then you get to E. So we're here. Then these transpose operations is because I need to realign the index, but E bar is basically the E times RT transpose. And I get this guy here. And then I concatenate this outcome, E bar, to my original input, X, and I create this matrix C. And then I process C column by column with my F0. This is the column index. And then the thing that I get in the output, it's a two-dimensional array. And what I do here is that I sum across across the columns, so across the number of particles, because it's 0 is the index, is this index, and 1 is this index, and obtain these quantities O bar that then I give as input to my last network. Okay. Last piece of crazy information about PyTorch, notice that the last layer, which normally we would end up with a sigmoid function, with a softmax function, sorry, because we want 5 probabilities, doesn't have the softmax. And this is because the cross-entropy implementation of PyTorch has the softmax included in the activation function, in the loss function. These are things you need to know, and unfortunately, so using PyTorch is not as easy as using Keras, which is the reason why Keras is very popular as a starting step, but PyTorch is way more powerful. If you look at TensorFlow, which is the code that Keras underlinedly uses, TensorFlow 2.0 was basically redesigned with respect to TensorFlow 1 to be an equivalent of PyTorch. So they are very similar now as languages. So out of this thing, you will get your 5 numbers, except that remember, this is before the softmax. And now, while in Keras, we just push the button and say, okay, model.train, boom, and it goes. Here, you need to say what's going on. So this code, you will recycle it if you want very, very often, but the structure of the code is always the same. So you divide your data sets in batches, you count how many epochs you want to do, and you allocate a tensor, a vector, which is a number of epochs, the loss for the train, the accuracy for the train, the validation, and validation. And then you loop over the epochs, and epoch by epoch, you fill the entries of these vectors. And then at each epoch, what you do is that first you do, so the optimizer is defined here, and it's Adam, and the loss is a cross entropy. This is the learning rate of the optimizer. And then what you do is that you zero grad, so you remove the gradients of the optimizer, so you're doing a new iteration. You compute the output of your model for that batch. You take the target of the very same batch, and you compute the loss given the output and the target. Here, you run the backward steps, so the computation of the gradients, and accordingly, you optimize the weights. And after you've done this, you compute the loss, and you fill the corresponding entry in your vector. Notice that here I'm doing some NumPy, some PyTorch magic. So basically I'm turning this object, which is a touch object, into an NumPy array such that it becomes a number I can handle. Is a question?
Hi, yeah. Is that a typical learning rate for GraphNets? I don't have any experience with them, but it looks smaller than I'm used to seeing.
I think that it came from some optimization the student did. There is another thing that you have to be careful. It's because since now, so basically, unlike Keras, now you are in control. In particular, I am in control, but this code is 2 years old. And all the conventions, you decide the convention. So for instance, in the loss, one needs to be careful if this is the average loss or the sum of the across the batch or not, because this changes the relevance of this scale. Typically, it's true, it's 2 orders of magnitude bigger, but I suspect that this is because we're playing with average and not with sums. There is an average somewhere. The students optimize that. So this is not necessarily you have like, but it's not super shocking if I'm thinking about it. I never tried to change it, honestly. So it would be interesting to see what happens.
Thank you.
So this is the training step. And if you look at the validation step, it has exactly the same syntax, except that it's happening on the validation data set and not on the training data set. And you don't zero the gradient because you're not doing any learning, and you don't do the backward step. So you don't optimize. You just compute the output, you have the input, you compute the loss, and you write the loss. And so out of this thing, you get the two vertices, the two vectors, which are the loss and for validation and training as a function of the epoch, which are the objects that we use to make this kind of plots, okay? Another thing is that now there is nothing like early stopping pre-built. So the early stopping is recoded here. And this is not a very super effective way to code the early stopping. As a result of this, my 800 epochs network actually went through 800 epochs. And this is why it takes forever. But you could define better ways to implement your early stopping. You can change the patience. As I said, you are in perfect control here. So you can decide your own algorithm by which you want to set to early stop, okay? And then after you let it go, it takes a little bit. You see this like 800 epochs. It's slightly overtraining. Notice that I didn't put dropout anything. I could have done it, but this is the kind of behavior. So the first thing that you notice is, number one, it's not clear at all that this training ended. So this training was stopped because it arrived at 800, which was the maximum number of epochs that I would say. But if you look at the thing, it still has a slope. It was learning. It was overtraining, that's true, because you see that the training loss is below the validation loss, but the validation loss is getting down, not as quickly as the training loss, but it is going down, which means that you are learning stuff. Not as much as you would like, but still you're learning. So this kind of training, if I see a plot like this, I would say, okay, I need to run more epochs, okay? And then the other thing that I would be worried of is that maybe if I keep going so much, at some point I overtrain. So there are two things you can do. Or you put breakings, like you save the model every, I don't know, 100 epochs, such that you can go back in case you overtrain, and you can do both. You put some dropout in the layer in between the dense layers. Okay, but then when you run the rockers, I think this is pretty striking with respect to the stuff that we've seen so far. Remember that here we're only using the first 30 particles in the jet. We're not using the full jet information. Regardless, I think these are the best results that we obtained this week. Why so? Because for some reason or another, why it's not really easy to answer, but as a matter of fact, empirically, we can assess the fact that this kind of architectures, not interaction networks specifically, but in general graph nets, fit very well the kind of sparse and permutation invariant data that in a typical high energy physics application you would handle. Okay. Now, here, as I said, you are in control. And so the number of things you can change in this thing, it's basically infinite. You can change the optimizer, the activation function, the this and the that. Here I've used Relu, you could use Celu. Someone played with Celu the first day, and so it's like a big improvement. I think that the same is true here. You can change the dimensionality. So for instance, here I'm taking 10, 10, 10, but you could decide to do 50, 30, 20. I don't know, it's just a matter of going there and hard coding numbers if you want. You can change this dimensionality here. For instance, you could expand the number of features which are learned. In the paper, I think we use more than that. In the paper, we did some Bayesian optimization that took a lot of time. The final model was, where is it? So this is the final model. So for the 150 parts, so for the 30 particles, which is our case, it's not very different. So for the 30 particles, we had, oh my God, what was this? Number of neurons. So this 10 here was actually 6. DE was 8, DO was 6. Okay, here is 8. And we use Relu, and Adam. And the optimized loss was 0.84. So this loss doesn't compare to this loss because I changed the code for this tutorial and I put some normalization factor here. And basically this is batch size independent. This number depends on the batch size we use, which I don't even remember how much it was. So you cannot compare directly these numbers here to these numbers here, but you can compare these numbers among themselves. Okay. And in our case, this was the best model we had. It's not, this is bigger than the one that we have, but it has more particles to start with, okay? And in terms of accuracy, you see that we're not very far away because 94, no, sorry, graph for gluon, 93, it's even better. Or is it? No, 95, and this is 93. 95, 93, and 91. So even with a smaller data set and a smaller model, we're already catching in terms of AUC, much of the separation power. Okay. Now, I know that this is a core dump of a lot of information, but I thought that it was good to give you a sense of what would be more a cutting edge level of application that you would be doing. I mean, there is a point in which you start to get familiar with these techniques. At some point, Keras doesn't serve you anymore and you need to do the step and do this. And yes, there's a question.
Yeah, thanks. Do you know if TF-Learn has GraphNet capabilities? PyTorch just seems really difficult to learn, and I'm sure worth it if it's the only option. But
so you can certainly take plain like hardcore TensorFlow and redo the same. I think I have it somewhere. I've done this exercise once to translate this to TensorFlow. It's in my GitHub somewhere. Let's see if I find it. Is it in my GitHub? I will have to look for it, but I have it. I have it somewhere. I need to find it. I think. But you can certainly do that. But as of today, I think the best way to handle this would be to oh, this is PyTorch still. Yeah, I'll look for it. I have it somewhere. I've done this. The best way, in any case, is to use these precompiled libraries, because the precompiled libraries have they optimize the math that is happening in the back. So if you look at this library, like GraphNet, the one by DeepMind uses TensorFlow, so this one. And you can just pip install it, and then the code is way simpler, because you see that it's similar to Keras. So this is the Keras of GraphNet in TensorFlow, if you want. It's not as easy as that, but you see that it's basically you allocate multi-layer perceptron, which are fully connected layers, and you do this kind of stuff, which is what the molecular evolution is what made GraphNets very famous. I suggest that if you want to start, maybe this is a good starting point. But I wanted to show you this because this is what's happening in the back, okay? And also because it might be that one day you will come out with your own architecture, then the only way for you to handle it is that TensorFlow 2.0 of PyTorch. And you will end up doing something like this. But certainly this is a good point. There is an equivalent of this, which is called PyTorch has the equivalent of this. So there is a library that allows you to handle GraphNets in PyTorch as well. PyTorch geometrics, something like that. I don't remember. But these are the options. And honestly, I didn't use this library yet, but I was told by one of the students took this very same data and tried to do the interaction nectar. Interaction nectar here, I think it's, one should have to look at the examples, but since they introduced interaction nectar, I think it's one of the pre-built architectures. It seems that with this library, it's way faster. Other questions? So, I mean, it takes a little bit to train, but it would be nice if you take some time to, it's 10-ish minutes. So if you take some time to try to play with this and try to see what you manage to get out. And so that we can try to assess the performance. So, and then maybe, because today was the last day we're playing with classifiers, tomorrow we'll be doing something different. So tomorrow we'll go back to Keras and we try to train an autoencoder to discover, so we will pretend that that we don't know about W top and Z's, and we try to discover them. And so we change completely page. So if you have time to try to do these things, it would be nice to see what you get. And also another thing is that since it's a lot of information that you're receiving this week, and I hope that the Slack channel will stay open, you can also come back to this when you have time, and then if I see the messages, I try to answer there. Still have 10 minutes, so if you don't have questions, I can actually show you some other application of this if you want. Nobody's saying no. So these are the same slides that you saw. I want to show you this. So this is what typically what people do with graph nets, like semantic segmentation. This is a semantic segmentation image from a convolutional neural network. The things that we discussed already for self-driving cars and so on, where you want to identify people, cars, and stuff. This is the same thing on an airplane, which has a less definite geometry. And in particular, the nice thing of a network like this, you see that the network learns that this piece of the airplane, and this part of the airplane, this part of the airplane, and these parts of the airplane are the same kind of stuff, even if they are far away from each other. And the reason why this is happening is because in the metric that these objects the network is learning, these pixels here, these bubbles here and there will be close to each other. This is what is called an edge conv. But the math that is happening is exactly the same that we discussed. It's the message passing algorithm. And people then build like layers of these things, the same way you have networks with many convolutional layers. You can have networks with many edge conv layers, but the idea is the same. And what we try to do is to use this, for instance, for calorimeters. So this is an idea of the kind of calorimeter objects, so that the kind of event that CMS will reconstruct in a luminosity C, where you're gonna have a calorimeter, which is effectively, it's layers of silicon with silicon sensors in between some kind of absorber, which I think it's tungsten. But so when you ignore the tungsten, because you cannot see there, what you're gonna see, you're gonna have this sensor that records some energy. So a way to represent it is this, so where each bubble is bigger or smaller depending on the energy that was allocated there. And here you have two particles that end up showering in the same place of the detector, and you want to separate them. And the problem is that the detector is completely irregular in its geometry. As I told you yesterday, there are, for those who were the discussion, these are hexagon-shaped sensors. The size of the hexagon changes depending on where you are in the detector. It's like a gigantic mess. But if you abstract away from it and you represent each thing like some coordinates of the hexagon and the energy that was recorded, then you can handle it with an edge conv. And this is the kind of stuff that you can do. The left is the truth, and the right is what the network is doing, and it's doing a pretty good job. And this is the same thing for pileup. Pileup is what happens at the LHC when you have a collision. Like you have some interesting collision, like you made a Higgs boson that gives you particles, like the orange particle you see there. But then you have other collisions are happening that make this diffuse noise that you can represent as dots. Each dot is a particle in E time phi. So this is the unrolled, the detector cylinder unrolled into a rectangle. And now for the charged tracks, for the charged particles, you know where they come from because you can track them, this thing that you see in the top. So for each of those dots, you know if they come from the interesting vertex of their pileup. And now you're playing the same trick as the social media example I was discussing, where basically you sit off on a generic particle, you look in the neighborhood to see if there are charged particles that come from the primary vertex, and there are charged particles that come from the pileup. And depending on where these particles are, how far these particles are, and how much energy they carry, you would like to understand, to guess if the particle that you're focusing on is pileup or not. And which metrics you could use, do you want to use to do so? You can come out with your metric. For instance, you must use something which is called PAPI, per particle pileup subtraction, whatever. And here we try to do the same thing, except that the metric we want to learn it with a neural network. And we did a message passing neural network to do so. So the thing that you would like to get is the thing on the right, starting from the thing in the middle, which is only looking at the neutrals, but you inject in the graph the charged particles that you know are pileup and those that you know are not pileup. And the structure is a message passing where you use a recurrent network to code the multiple steps. And this thing I showed you is that you do it like start from the first neighbor and then second neighbors and third neighbors in 3 iterations. And it's interesting in the sense that, so if you look at the PAPI and soft killer are the 2 algorithms that people typically consider, and they have their good and their bad behaviors. So PAPI typically is more complex than soft killer. Soft killer is basically applying a flat threshold on the event. So everything above some energy threshold is okay, and everything below is ignored, except that this threshold changes depending on the topology of the event. So there is an algorithm that decides where to put the threshold, and then you apply it flat. And what happens is that when you have isolated stuff, like if you look at, if you look here, when you have isolated stuff which is energetic enough, you will call it these guys interesting while they are pileup. PAPI knows how to remove them. PAPI has the other problem though, is that when you have stuff which is close to interesting stuff that is soft, it will not remove it, while soft killer does. And our network manages to handle with both cases. And in my mind, this is a better way to handle the problem, but we didn't manage to convince CMS to adopt it yet. I mean, we have time. We have 10 years. And so this is another thing. And then I close it. This is another kind of network that we want to use for the same problem of before, for the calorimeter problem, except that we are handling the problem that was raised before, which is the memory consumption. So we would like to build something in which the graph size doesn't explode. And a way we do this is basically enforcing, so we build the same paradigm of the message passing, except that the message is written down as an analytical function, for instance, an exponential potential, e to the minus d squared, where d is the distance. And this distance is in some, it's the Euclidean distance, but in some abstract space, which is learned by a network. So you take your physically arranged calorimeter hits in your detector. Each hit is processed by a neural network that defines some new coordinate system that you learn. And in this coordinate system, you compute the distance, and then you use an exponential function of that distance as a weight, as a message. And then you do the same stuff. Now, these networks are linear. There is no activation function, nothing. The nonlinearity of this processing comes in this potential here. So what we want to do is that we want to promote things which are close by, and we want to suppress things that are far away. But close by and far away are obtained from some linear transformation of the inputs. We could put also an activation function here. Still think we should, but my collaborators are not convinced. But the nice thing of this is that you can get similar performance. So this is the mean response and the variance of the response for the different models. DGCNN is the EdgeConv. EdgeConv has the best behavior for the resolution, not for the bias. It has a bias as a function of the true energy. And to me, the best option is this Garnet thing, because it has comparable results to the blue, to the orange, to the blue. It has comparable results to the blue, but it's slightly worse in variance. But if you look at the memory footprint, it is like super small with compared to the other ones. And the reason why this is though, because it's different networks than the previous one. It's not connecting each vertices to themselves, but it's connecting vertices to another kind of object which you call aggregators. So you basically tell your network how many aggregators you have. And so the message is passed from the vertices to the aggregator, and then from the aggregators back to each individual vertex. So if you have n objects and k aggregators, the complexity here is n times k, the size of the matrix. So typically k is way smaller than n. So this goes linearly with n, and the memory consumption goes linearly and not quadratically with n. And so this object here we managed to put it on, we could run this on the level 1 trigger. Well, the other ones, there is no way we're gonna run them on the level 1 trigger. And I think I close because it's 3 p.m. If there is some last question.